So welcome to Physics 30 Prep Fast Track, Lesson 12, your last two-dimensional motion example. In this example, which is a difficult one, a ball is projected with a speed of 15 meters per second at an angle of 35 degrees. That means that it's not moving horizontally only, but also moving vertically. So we need to, of course, break that down into its two components. From the top of a 2.5 meter shelf and hits the ground below, how long is it in the air, and how far from the base of the shelf does the ball land? Now, the reason this is difficult is that the time of flight is not easy to determine because the initial horizontal velocity is not zero, and the initial vertical velocity at this point is a certain amount. It's going to be much greater at the bottom of its trajectory. So the initial vertical velocity is different than the final. So what we need to do is we need to find our velocity, both horizontally and vertically. In order to get the time of flight, we're going to have to look for more information. We don't have quite enough information vertically to do it right off the bat. But we will need to find the initial vertical and horizontal components. Just like we did in the previous question, we need to resolve those vectors into their components. All right, the 15 meters per second at 35 can be found using trigonometry. Then the final vertical velocity is something that we will need. All right, we didn't need it in the previous example, or we could assume that it was the same as the initial. Now we need it, or some other method, but let's stick to that. And then we get the time of flight, and finally we'll get the horizontal displacement. So each step will be shown in the following example. So each of these four steps: resolve the initial vertical components resolve the initial velocity into its components, find the final vertical velocity, the time of flight, and finally the horizontal displacement. So the first thing we should do is resolve the initial vertical velocity into its components. And we did this with a previous question. We would just say, okay, here's our 15 meters per second at 35 degrees. The vertical and horizontal component need to be found, and just as before, because we're using the same numbers, we get the same result. That the opposite, or the vertical component, is hypotenuse, or 15 times the sine of 35, 8.604 vertically. So that's right here. We know the vertical initial velocity vertically is 8.6. Horizontally, we can find it, and of course we found that it is 12.287. So those two are necessary. That's step A. Now we can use that initial vertical velocity to find the final vertical velocity. Because we know the displacement and we know the acceleration, that's our next step. So use the vertical information to find the final vertical velocity. The reason for this is that if you tried to solve for time using d is equal to VIT plus 1/2 AT squared, if you tried to use that formula, you would find that because the t is in two places at once, it's difficult to solve for. You would have to use the quadratic formula from Math 20 or Math 30, and it gets a little bit messy. It's a challenge, and some of you, I'm sure, are capable of it, but there's an easier method, and that's step B here. So what we do is vertically, we say, okay, the initial vertical velocity is 8.604. We know that the acceleration is negative 9.81, and we know that from the time, the point of release to the point where it hits the ground, vertically it's gone down 2.5 meters. So we know that the vertical displacement is 2.5 meters. Now this is a little typo here, just please be patient with us. That should be negative 2.50 meters, not meters per second. So a little mistake there. Anyways, when we resolve this and solve for VF squared, we get VF squared is equal to 8.604 squared, the initial squared, plus 2 times negative 9.81 times negative 2.50 meters. And what we get is a 123.07, but that's of course VF squared. When we find the square root, we get 11.09 meters per second down, or in other words, negative 11.09 meters per second. So make sure that you understand that initially this was positive because it was going up, but now we have a negative value because, of course, at the final point it's going down, and so it should be negative. So keep that in mind. We'll need that for the next step. And of course the final velocity can now be used to find the time of flight. So this is C in our step-by-step solution. So using the vertical information to find the time of flight, now that we know that the final velocity was negative 11.09, we can use that here, all right, and we can solve for t. And there's a number of different ways to solve for t. Here's the most likely candidate. There's probably one more method, or maybe even two, that you could use. So if you do it another way and you still get the same result, then that means you've done it correctly. So there are sometimes different avenues you can go down here, and they're all usually acceptable as long as you're following proper algebraic methods. So VF is, of course, negative 11.09. VI was positive 8.604. Now the change in velocity wasn't 11 minus 8, it was negative 11 minus 8. So almost 20, 19.6 or so. And so, of course, that gives us negative 19.7 meters per second. That's the change in velocity. Divided by the acceleration that caused it gives us a time of 2.008 seconds. And that is our time of flight. So now that we know the time of flight, we've answered A. How long was the ball in the air? 2.01 seconds would be a good answer. And of course, we need now to find the final answer. How far from the base of the shelf does the ball land? So, using the time of flight and the horizontal velocity from step A to determine the horizontal displacement, again, we look at it horizontally. We remember that the initial horizontal velocity was 12.287 meters per second. Since there is no acceleration of gravity acting horizontally but only vertically, the horizontal velocity won't change unless there was something like air friction or so on. But ignoring air friction, we know that the constant velocity horizontally is 12.287. We know that the ball was in the air for 2.008 seconds. So since V is equal to d over t, then dH, or d horizontal, is equal to VH times t. 12.287 times 2.008, and we get 24.67 meters, and that would be rounded to 24.7 meters. So the ball lands 2.01 seconds after launching. That's the answer to A. And it lands 24.7 meters from the base of the shelf. This is an excellent kind of question. If we were to do a lab in this course, this would be one that we could shoot a projectile into the air at an angle, and we would, of course, predict where it might land, and then we would do the test, and it works quite well. So there's all your examples for two-dimensional motion. The first one was a simple object rolling horizontally off a shelf. The second one was an object being kicked on a horizontal field. And the third one, a little more complicated, an object is projected at an angle from a different height than the landing point. So those three types of questions, especially the first two, are very much an important part of the Physics 20 and prepare you for 30. And the third one is a little bit of a challenge, but you should be able to work it out following the 4 steps that you were given in this example. Alrighty, now we move on to force.